Okay, so now we've talked about alcohols and ethers and how to name them. Now we need to know how they behave. So when we talk about physical properties, it's important that you realize that what we're really talking about is like if you have a whole bunch of that molecule, like a cup of it, how does it behave? How does that cup of stuff behave when they're all together? So what you're really looking at is how they interact with each other. So we're not just talking about one molecule here. We're talking about how different molecules interact with each other. So in an alcohol, sorry, I put this side note in here. In an alcohol, you have an OH group. An OH group has hydrogen bonding possible, right? Because then oxygen attached to a hydrogen, that's what happens with it. Versus an ether doesn't have that hydrogen. So this guy can't hydrogen bond to anything. That's going to make a difference into what it can do here in a minute, because this one can hydrogen bond. Remember, hydrogen bonding is a very specialized version of a dipole-dipole bond, and these are what happen between molecules. Hydrogen bonding is the reason why water is not gas at room temperature, because water sticks together really well with other water molecules. Okay, just a side note, when you're looking at alcohols, see how that carbon is attached to that alcohol? However many carbons are attached to this kind of gives rise to how substituted that carbon is. What that means is this would be like a primary alcohol, a secondary alcohol, and a tertiary alcohol. It doesn't have to do with substituents, it's just that we refer to that as a primary, secondary, and tertiary because this is attached to one other carbon, this is attached to two other carbons, and this is attached to three other carbons. It doesn't matter what else that is. That's something we probably will talk about later. So now, back to the hydrogen bonding versus no hydrogen bonding. Let's look at the boiling points of these two compounds here. Notice that they have the same number of carbons, they have the same number of hydrogens, they have the same number of oxygens. The difference is this guy is an alcohol. He's an OH. He can hydrogen bond. That means that he sticks to other parts of an OH in another molecule of the same type of thing pretty well. That's pretty sticky stuff between molecules. That's the reason why this boiling point is so dramatically higher than when you don't have that OH. That's the power of hydrogen bonding. Okay? When we're talking about boiling or melting points, just want to make sure that everybody's on the same page here. This is talking about how molecules stick to each other. When you boil things and you melt things with covalent bonds, you are not going to break the covalent bonds themselves. What you're doing is you're breaking one molecule apart from another, the way that it's packed. So like in a solid, you have boom, boom, and they might go like this a little bit to go to a liquid, right? And when you go from a liquid to a gas, now they're like, whee, over here. Okay? So it has to do with how the molecules interact with each other, not necessarily within the molecule. Okay. We've also talked about how like dissolves like. But what does that really mean? It's easier to see when we talk about an alcohol. Because an alcohol, remember this R means it can be anything. An alcohol has a chain of carbons, and it also has an OH group. So, this guy looks like water. This guy looks like oils and hexane and things that are alkanes. Well, the longer this chain gets, the more it looks like those hexanes and alkanes, and the less it will dissolve in water. But it'll be better at dissolving at things like hexane and nonpolar things. But if this is a shorter chain, then this represents more of the overall percentage of the molecule, shall we say? And this is polar, and therefore this hydrogen bond will stick things together better. So when it comes to solubility, what we're really talking about is how soluble is something. How much of A will dissolve in B. Now you can do that with anything from salt and water to Play-Doh and dirt. Maybe. But you get my point. Okay? Ethanol is going to dissolve very well because it's a very short carbon chain in water. But say if you get like octanol, decanol, things like that, where the carbon chain's really long, it's not going to dissolve as well in water, but it will dissolve better in nonpolar stuff. Now, ethers that don't have that OH group, well, they actually will not dissolve very well in water, period. If they're pretty small, then maybe they will some, but since they don't have that OH, it really makes a difference. They will dissolve in more nonpolar types of compounds, however. Okay. Now let's look at some reactions. When I talk about a dehydration of alcohol reaction, this is really just the reverse of what we just did. So before we were taking an alkene and adding water to it. Well, if you heat that up and you have enough acid in there, the exact opposite will take place. So if we have an alcohol here, by adding acid and heat, we end up with the alkene. So let's look at what that's doing when we consider all of our hydrogens and carbons and stuff here. Okay, so I've got 1, 2, 3, 4, just like you have up here, 1, 2, 3, 4. There's the OH. Now, I purposely made it so that these are pretty far apart because I want you to just realize there's an OH coming from this carbon right here, this one. And there's another hydrogen that's being removed from this carbon next door. It's not these two, it's these two. Could you draw this down here? Absolutely, and then it'd be a little circle right there. That's fine. But just make sure that you're doing that between these two carbons. And what that means is that's going to give you a double bond right there, because as this bond gets removed and this bond gets removed, there we go. Can you see how that's going to make 2 hydrogens and an oxygen? Well, guess what? That's water. And there you go. Sometimes we don't even write this. It's still there. We just may not write it. And the reason being is that we're focused on what that organic transformation really is. So don't let that confuse you either. If you want to write it because it makes you happy, feel free to do that. So what if we're given a choice? This OH could combine with a hydrogen from this carbon, or it can combine with a hydrogen from this carbon. Well, we don't make the rules. We observe as scientists and try to figure out what's going on. And what we've observed is this will give you mainly that as a product. What that means is we're removing a hydrogen preferentially from this this carbon right here over this one. So after further study, basically what we've determined is that the carbon with the most other carbons attached to it, if there's a hydrogen there, that's the one that's coming off. You could also see that as the carbon next door with the least number of hydrogens. But that's kind of harder to see when you're in this format, so be aware of that, okay? You can't remove a hydrogen if there's 3 carbons coming off of that, because there won't be one. So just be careful with what you're doing here, okay? So this carbon right here will remove a hydrogen from the carbon next door in this direction because there's more carbons coming off of him. Over here, there's only 1 other carbon coming off of him, okay? And that's why we end up with a double bond right there. Okay. The last bit here, I just want to expose you to, so because it will kind of help us in our next section here. There are terms of that we should know. Oxidation and reduction are some of those. The easy way to identify an oxidation reaction in organic, and this is way oversimplified, but it kind of works for our purposes for right now at least. The more bonds you have to oxygen or sulfur, honestly, that will work as well. In a reaction, the reactant just became oxidized. That's an oxidation reaction. If you have fewer bonds to oxygen in a reaction, or sulfur, that's the same thing, the reaction was reduced. That's a D. U, C, E, D. Sorry. So here I have, and what I mean by bonds is bonds between carbon and oxygen. So let's make sure we know that. More bonds to oxygen from carbon, because obviously there's the same number of bonds to oxygen either way, sorry. So here we go. We've got one bond between this carbon and oxygen, and look here, now we've got two. That's an oxidation reaction. Here I've got two bonds between this carbon and oxygen, and here I've got 1, 2, even though this is a separate oxygen, we sort of count that. This would be adding more oxygen, therefore that's 3 bonds to oxygen. That would be an oxidation reaction. Keep in mind, I'm grossly oversimplifying this, so roll with me, okay? Another way to look at this is with sulfur. So here we've got 2 thiols. If we reduce thiols, you can make a disulfide bond. There's other ways to reduce it, but this is one of them. The cool thing is here is that this is kind of how we can make perms in our hair, and disulfide bonds are used in the body quite often. Sometimes, I should say. Okay, so this would be an oxidation reaction because we're having a sulfur-sulfur bond right there. Reduction is going to be the opposite. So here we've got 2 bonds between this carbon and oxygen. If we reduce something, that's going to go down to 1 bond. Here I've got 1, 2, 3 bonds to oxygen from this carbon, and over here I've only got 2. That would be a reduction reaction. And the same is holding true for the disulfide bond. To go back to where it was before, that would be a reduction. Again, just exposing you to these, just be able to recognize them. I'm not asking you to know what types of reagents you use there. Thank you very much.